Okay, so right, so I'm going to give a second talk. So this is the I'm recycling the talk which I gave in Aspen like a couple of weeks ago. Yeah. So and then, but yeah, it's about integrability. So like integrable systems and connections to representation theory. It has somewhat physics title, but it's not like yeah, it's essentially it's going to be a math talk. So q-Opers and as geometrization of n equals 2 theories. Now here's the list of papers. So my collaborators on this project are Anton Zeitlin from Louisiana. So I just came back from there on Tuesday. And yeah, so my previous talk was recycling of that seminar, then Edward Frankel and Daniel Sage. So Daniel Sage is also from Louisiana, and then will be, and Ed is here at Berkeley. They're all faculty members, yeah. And this is a program of understanding geometry behind integrable systems of two types, spin chains and many-body integrable systems, like Calogero or Rosinars, and spin chains like XXZ, XYZ, XXZ. And yeah, so basically the duality between these two types of systems was, in the literature for quite a while, but like only now we actually understand how to put it on geometric footing. So there are various motivations we can think of. Yeah, so the first one is sort of understand the geometry behind integrability, behind integrable systems, and this paper was cited several times in this workshop. Aganadich Okounkov, and well, previous work by Andrei Okounkov on quantum geometry, equivariant K-theory, and equivariant quantum homology, and then sort of I joined in with these people, Pushkar, Smirnov, and Zeitlin. So Smirnov spoke earlier at the workshop, and then we developed we wrote a paper together on quantum K-theory and Nakajima quiver varieties and many-body systems. So in a nutshell, I'll show you the results soon, so that if you study some nice symplectic resolution, like sort of quiver variety, which is sort of symplectic resolution, like a cotangent bundle to some nice space, then it's quantum K-theory, or like basically some quantum geometry of that space describes naturally the many-body integrable systems. So for example, n-particle RS model, Roizen-Schneider model, arises naturally from, basically the coordinates in TRS are some quantum classes. Sorry, there are some, K-theory classes, some bundles. I should rephrase it. No, sorry. Coordinates will correspond to, in one frame, twist parameters or the Kähler parameters of the quiver, and the momenta are certain quantum classes, right? And the TRS energy relations arise as certain relations in quantum K-theory. Yeah, so next is this BPS CFT correspondence, sort of physics motivation by Nekrasov and Shtashvili, so you can sort of generalize it to geometry. Then most mathematical part here is the quantum geometric Langlands, or rather Q Langlands, when in quantum Q Langlands, you would study a correspondence between the conformal blocks of some quantum toroidal algebra and some doubly deformed W algebra, but you can also study at critical level, right? So in the semi-classical limit, when you take critical level limit, this correspondence becomes classical, and that's like what I'm going to tell you today will be an example of that. So you'll get sort of Opers on one side and q-Opers and the beta ansatz on the other side. And another part is this ODIM correspondence by Bazhanov, Lukyanov, Zamolodchikov, and then Dorian Tuteo. So here you would study spectrum of some differential equation, matrix differential equation with some singularity, right? And then, well, there's some other terms here. And then you would ask the question, so what are the eigenvalues of the monodromy matrix, right? And it turns out that this monodromy problem, so it looks a little bit like Riemann Hilbert, right? So you would look at the monodromy problems of this differential equation, and then you discover that the like if you look at this monodromy of the fundamental solutions, then they're parameterized by the fundamental solutions are parameterized. The coefficients in some basis in this set of fundamental solutions are certain q functions, q and q tilde, and they form the QQ system, which is equivalent to beta andas. So that's another kind of example of this quantum classical duality when there's a quantum integrable system on one side and classical integrable system on the other side. And then right now we're working on a paper with Frankel and Zeitlin where we sort of essentially connect this to what I'm about to tell you today. But yeah, it's not going to be in today's talk. Are any quick questions about motivation? Okay. So now, yeah, let's talk about let's talk a little bit about this q varieties. So the q varieties. So what is a q variety, right? So for a string theorist, it's a very kind of straightforward construction. Well, then you can basically look at the various branes, right? And the look at fundamental strings that are stretched between these branes, and they provide a representation theory data for the quiver. So basically, these are some linear maps from various spaces. So for example, if you have space of harms from well, one vector space to the other, you would just study the space of strings between which are stretched between stacks of one type of branes and stack of the other type of branes, and then there are three types of maps, right? So basically there is so W corresponds to framing here, right? And then this is something that you fix, right? And then there are also strings between various gauge nodes here, right? So there's home Vi to Vi plus 1, and then there are sort of self homes, right? So from the vector space to itself, right? And then you can draw this brane diagram. Basically, then so this red branes are called D5 branes. So if it's the first time you see it, just think of it as a certain prescription, certain notation for the q variety, right? So because I'll use this picture to illustrate the duality between spin chain and TRS system in a bit. So here you would take the yeah, so like basically these numbers. So if you have 3 here, there are 3 D5 branes and so on. So I hope the notation is self-explanatory. So basically we have this domain walls, they're called NS5 branes, and then there are some D3 branes between them, and then D5 branes go like this. And yeah, so that's sort of the physics picture. So mathematically, you would study the moment map, right? So you take, so let G be the product of all groups in gauge nodes. In this case, it's U1 times U2 times U2 and so on. Yes, the number here means it's a unitary group of that rank, not SU, but U, right? So there's certain preference in using unitary as opposed to special unitary. And you take the dual of the Lie algebra of G, right? And then the moment map is the map from cotangent bundle to the space of all representations. So basically you take all this linear algebra data, you compose it together, and then you sort of double the arrows, right? And then the q variety is this GIT quotient of the inverse of the 0, right, of the moment map in the presence of some stability conditions. So it's my understanding that Andrei Smirnov talked about those a little bit in his talk. Also, algebraically, it's a certain stack quotient where you have a semi-stable locus of the space, and then you mod out by G. So here's an example. If you have K and N, then so it's a quiver of type A1, right? Because it's like, Dynkin diagram for A1. There's one circle, one node. And yeah, so this quiver corresponds to cotangent bundle to the Gersmanian of K hyperplanes in Cn. Yeah, and this is the automorphism group. And then classical K theory of X, so let's call X is q variety. Let's call it X. Should we call it X? Is formed by the tensorial polynomials of tautological bundles and their duals. Right. So basically here there's a tautological bundle of rank K and then of rank N, and then you can also dualize them. So as an example, and then yes, so an equivariant theory is the module over the ring of equivariant constants. So for each framing, you can look at the maximal torus of the of the automorphism group, right? And then those A sub i's are the equivariant parameters which appear in localization, right? So it's a equivariant K-theory of the point, which is this ring over here, and then H bar here. It's also very important. So this H bar is not that, well, I mean, it's a Planck's constant, right? It will be some quantum parameter in the spin chain, but yes, so here it's the equivariant parameter which corresponds to the C star action on the cotangent fiber, right? So you have a cotangent bundle there, you can just dilate the fiber with weight H bar, right? And it also similarly expands the symplectic form. Yeah. So as an example for this Grassmannian, for T star Grassmannian, you have, so if you take this K-theory class V tensor squared minus third exterior power of the dual. So V is the bundle, tautological bundle for this for the gauge node, and the corresponding class tau is given by this polynomial, right? So that's the classical tautological K-theory class. The classical it's a class of equivariant K-theory of the space, and then you need to also think if you have the framing. So those AJs are the framing fugacities, framing parameters. Then this is the relation that you need to impose. So basically, it looks like if you expand the polynomial, you will see that you have the symmetric polynomials. There are symmetric relations on those. So SIs are this correspond to each of those bundles, right? So and then basically S1 to Sk Chern roots of the tautological bundle. Yeah. So that's classical relation. Now, in quantum K-theory, you would study a space of quasi-maps into the square variety. So like here, it's an example of variety of type A. And this is what is AN quiver variety with framing, right? And then so you would integrate over the space of moduli space of quasi-maps from CP1 in this case into quiver variety, and so it's a certain equivariant integral. It's an equivariant K-theoretic push forward when we take the sort of so like you have to look at the equivariant action on the curve, right, on CP1, and there are two fixed points, 0 and infinity. And then sort of here it's shown how a typical evaluation of quantum K-theory class goes, right? So you take the class tau, like an example from the previous slide, you would evaluate it, say P1 is 0. So you evaluate it at 0, and then you do this evaluation at infinity, right? And then you do so star means it's the push forward. So you do you're doing the integration. So in physics terms, so think of this as a think of it as the correlator. So say tau is your BPS observable in your supersymmetric theory, and it's basically it's a localization computation of that BPS observable. So and then basically
Sure.
Yes.
In the second expression, where is the Q?
What is Q?
In the second expression, Q? In the second.
Here?
Yeah.
Oh, it's well. I mean, it's in the. I mean, it's the. No, it's like. So Q only arises in the. Oh, I mean, it's a description of the stack of this moduli space of quasi-maps. So QMD means it's a quasi-maps of degree D, which are non-singular at P2, right? And then part of the so when you compute characters, like there's a Q, you would compute Q characters, right? So like they would arise here for it will appear in this hypergeometric fashion in this calculation. So here it's basically an inner product of this class times this class. Yeah. So then basically you can compute this observable, and then you can ask what happens as what Sabiok was asking as Q goes to 1, right? There's a semi-classical limit of the story, and then what happens is that this variable, this function V, which is called vertex function, behaves as exponential to 1 over log Q times some function W tilde, which is called twisted superpotential. And then so this function would depend on Churn roots of the bundles, like this S's from the previous example, and also on the equivariant parameters. So if you ask yourself, what is the Jacobi ring of this function? So find this. So you differentiate it. If you find the minima of the space of solutions, dw over ds is equal to 0. You would sort of extremize it with respect to all churn roots. You'll get some polynomial. You'll get some equations, right? So in other words, you need to write it like this: it's e to the dw tilde over dsi, right, is equal to 1. So the way this w works, it's some logarithm, and basically when you do this calculation, you're going to get a polynomial of those churn roots. So so that leads us to this beta and nuts equations. So if you denote with q, so I'm already introducing this q function. So if there's a q function of u with whose roots are, let's call it s. Right? So if you look at this quiver, for every node there's a double index, right? So there's a node corresponding to the index corresponding to the node, and there is also index within this space. Right, so there's a product like this. So for every vertex, for every gauge node, we have a q function, and then so lambda here is the framing. So for every framing node, we have lambda function. I think it should be u here, right? So z, and z is an auxiliary variable, right? So then so the saddle point equations will look like this. It's a beta and nuts equations for x-axis spin chain written in this QQ form, right? And then sort of another sort of standard fact from integrability is that these equations can be rewritten as the so-called QQ system. So you would so it's so essentially there are two types of q polynomials, q plus and q minus. So here this one is q plus, and then the q minus is an auxiliary polynomial, which is not, in a sense, it's not physical. So its roots, they do not appear in the spectrum of the spin chain, but well, its role will be clear later when I'll talk more about the QQ systems. So yeah, so this is kind of the equation that we'll be analyzing in the main part of the talk. Any questions? Okay, but that was more or less a reminder. So it's not like, now let me formulate the duality that I was sort of anticipating before. So there's this quantum classical duality between quantum systems like spin chains and classical systems like TRS model. So here's the physics approach. So for physicists in the room, so again, take a quiver and consider its quiver diagram, this Hanani-Witten types of quiver diagram. And then what happens is that, so there's a module here, like you can move those brains along this direction. Now, we can almost do it without any penalty, except that whenever this red brain, D5 brain, passes through an S5 brain, we need to stretch this D3 brain. So it's like a foam, right? So when you move the frames through each other, and if there's a foam, then like you would see this like another plate of foam will form, right? And then it will stretch indefinitely. So here, and then you can think of you can also calculate what I call linking numbers, right? So like as you move all the D5 brains to the right and all NS5 brains to the left, you can count how many brains each on how many D3 brains and on each D5 brain and on each NS5 brain, and yeah, so that gives you some data which we call linking numbers, and then sort of the key observation comes at the step is that these two pictures, they provide different descriptions of the same system. So there's a three-dimensional description given by the quiver, right? So basically you live in 3 dimensions and you study, so sort of geometrically you would study quantum equivariant K-theory of the corresponding quiver variety. And on the other side, you have if you think of this picture as an interval in this additional direction, then it's a four-dimensional system. So it's a four-dimensional theory on this interval, right? Subject to certain boundary conditions which are consistent. Now, it was known for some time ago from works by Gorsky and Nekrasov and Danagi and Witten that this theory here, the vacua moduli space of vacua of that theory describes the this phase space of describes the Kalogero-Moser space, right? So and the which will in the complex structure that I will be considering today, J will give us the Roisenar-Schneider Hamiltonians as opposed to elliptic Kalogero. Again, it's a hyperkähler space, as I mentioned in my previous talk. So we'll be utilizing it in complex structure J. But for us, what's important is that it provides this interesting duality between, from 3D perspective, have quantum K theory on X on a Q variety, and from the 4D perspective, we'll get this new description in terms of many bias system, in terms of Kalogero-Moser space, and then these defining relations from CM space, which Oleg Chalich wrote yesterday, and I'll remind them to you in a couple of slides. They describe essentially the same system. So this condition on the Kalogero-Moser space are one-to-one in one-to-one correspondence with the beta equations for the spin chain. Right. So and then geometrically it allows us to prove this theorem that the quantum K theory of the space X is the following quotient. So it's a algebra, complex valued algebra of some generators, where P, so there's C will be the coordinates in TRS model, P will be the momenta, and then AI equivariant parameters. And then the relations in the ideal is just the spectral curve of the TRS model. Questions? Okay, so right now here's a reminder of the Kalogero-Moser space. So let V be an n-dimensional vector space over C, and then M prime is a subset of GLV cross GLV cross V star that consists of elements M, T, U, and V. So M, T, and matrices in U and V are vectors, such that the following relation is true. So Q, the parameter, and then there's like a Q commutator of matrices M and T is equal to matrix of rank 1, right? And then we want to consider this modular conjugation, right? So you can conjugate the matrix from left and right, and then we can multiply by these vectors on the left and on the right respectively. And then the quotient of the space by action of GLV is called Kalogero-Moser space, right? So it's algebraic stack. So if you think from algebraic point of view, yes. So and then I described this in more detail in my first talk on Tuesday. Yeah, but for us, what we need here is that just look at the, so basically M and T. So one of them will be the lax matrix for the TRS model. Right now, again, as I was explaining earlier, you can think of this space as the character variety of the puncture torus, right? Where the like the data on the puncture, like it's the monodrome around the puncture has only one eigenvalue. And you could also consider some generalizations. So integrable Hamiltonians are traces of this, the Casimir's traces of this matrix T. Okay. Now, there's a whole hierarchy of models, which are, so here the TRS model lives in the middle of this. But yeah, so you can ask yourself, okay, so we know that there are rational trigonometric and elliptic systems, and you can make it rational trigonometric and elliptic in both coordinates and in momenta, right? And then there's this diamond here, 3 by 3, where all our favorite models put in them. So TRS is trigonometric in both, right? And then you can basically there's some sequence of limits, so you can travel between TRS and trigonometric Kalogero, and then rational Kalogero, and then rational Roisenars, which is dual to Kalogero, and so on. And then of course, yeah, so like if Shamil would be here, he would be talking about this model. So like on top of hierarchy of this hierarchy, there is a del system, right? So del stands for double elliptic, right? So the joke goes that del is not a computer, right? And I'm sure maybe some of you are working on a Dell computer right now. Yeah, this one is different. And then yeah, so I see Sasha Gorsky is here, but Sasha will be talking about something else, right? You're not going to talk about Dell, right? Okay. Okay, so the summary of the quantum classical duality before I'll talk about Opers is this. So you have on the quantum side, there's a spin chain of XXZ type. So it's an SUN XXZ spin chain. Like this example, this is a particular example when I choose a proof variety, which is the cotangent bundle to the complete flag. But in terms of integrable systems, I just wanted to summarize what the correspondence looks like. So there's a spin chain periodic with periodic boundary conditions which are twisted. So there's a twist matrix which we use to identify the ends of the spin chain. And then the twist eigenvalues are called z sub i's. And then we have, it's an anisotropic spin chain, meaning that the interactions between spins are not equal to each other. So like strengths of interactions are different. And then this is dialed by so-called equivariant parameters, so anisotropy parameters, AI. So these are equivariant parameters from K-theory construction. And then there's a Planck's constant, right? So the beta equations look like this. It's a system of polynomial equations, which kind of you can usually write as fractions, and you can write them as this locus, the critical locus of the of what is called Yang-Yang function, which is the superpotential. Good. So you find those beta roots and you plug them into expression for the energy. You find the spectrum. Now on the classical side, we have n-particle trigonometric Rosiner-Schneider system. So where the coupling constant is h bar, so it's the Planck's constant from the spin chain story. Here's the example of the first Hamiltonian. Again, we've seen this many times already in this workshop. And now the coordinates of TRS are the twist variables, and then this energy levels, eigenvalues of TRS Hamiltonians, are elementary symmetric functions, elementary symmetric polynomials of the equivariant parameters. So you would, and then so yes, like you have symplectic, yeah. So these Hamiltonians commute with each other, right? So they have common set of eigenvalues, right? Okay, we're talking about classical stuff, but anyhow, so you look at the energy levels of these Hamiltonians, and then the statement is that the set of solutions of these equations is in one-to-one correspondence with set of solution of those. Yeah. And under this correspondence, for example, the P, the TRS momenta, Pi are equal to a certain certain products of beta roots on the neighboring vertices, right? So on the neighboring nodes. So you have SI1 times SII divided by SI minus 1, I minus 1, I minus 1. So symmetric combination of those Chern roots, and then you divide by the other. So that gives you the TRS momentum. Questions? Okay. Now, yeah, then look at one more sort of piece of geometry here. So you can sort of put it on a very robust geometric footing. So consider the Kallager-Moser space M and its copy, where instead of yeah, basically we have two types of variables, AI and ZI, and then in fact there are two frames. There are two different TRS models. In one of them, the coordinates are z's as here, and the energy eigenvalues energy is related to equivariant parameters to a's. And then there's a so-called mirror frame. We can swap them around, and then coordinates will be ai's, and then the energies will be related as via the functions of these parameters. So you can do this. You can put these two systems together, right? And then the we can draw the Lagrangian submanifolds. Yeah. So first of all, consider the symplectic form omega. So we have A's and Z's or zetas, right? So it's two sets of variables, right? And then we'll put them all together. So it's a big symplectic manifold of dimension 4n or complex dimension 2n. Then these TRS momenta are exponentiated derivatives of the y function with respect to either zetas or A's respectively, right? And then we can draw these two Lagrangians in the phase space, in this big phase space, which would intersect transversely. And well, what the correspondence shows is that, well, one of the Lagrangians, sort of the conditions for L mu, they fix eigenvalues of M from the definition of the Cauchy motor space and impose so-called slot-away slice on T. So it's a certain form of the matrix which involves the highest weight vector and the raising operator. It's like you would consider an embedding of SU2 into your GLN, and then it's certain presentation of the matrix. Let me not go into this. And L tau, the other Lagrangian, it fixes eigenvalues of T and imposes slot-away slice on M. So in general, those two Lagrangians wouldn't intersect transversely, and then, well, you can show that the intersection points will correspond to solutions of beta equations. So here, this twisted superpotential and its dual are equal to each other. Okay, so that's this is XXZ TRS duality. It was in the literature for a while, but now the question is, can we generalize it? Can we make it more general? So can we go beyond so basically, is there anything beyond that which sounds similar in spirit? Are there any questions? Okay, yes, 1 second. Okay. Great. So now I'm going to set to the second part of the talk, which is well, let me skip this. So I'll explain how the generalization goes by using the using the notion of q-Opers. So q-Oper will be a certain gadget which will generalize the TRS model, the classical integrable system, and then on the quantum side we'll still have a QQ system as an XXZ chain, but it will be more generic. So here's the so if you kind of or if you're just joining in, it's okay because you can start listening to this part of the lecture from scratch, right? It does not use anything from before. So consider a vector bundle E over P1, right? And then map M sub Q from P1 to itself, which just dilates the coordinate Z like this. And then, so that induces map of vector bundles from E to EQ. So there's notion of grading. And then sort of we want to understand how this linear map looks like in some trivialization. So if this A of Z is a GLN C-valued matrix, right, depending on the coordinates on the base, then as we change the coordinates, right, so the if G of Z is an element of GLN of C of Z, right, then this map will go through this change of transformation. So A will go into G of QZ times G inverse, right? And this is the difference Q analog of normal gauge transformations that we know and love from Lie algebra theory. And so, and then for every linear map between bundle E and bundle EQ, we can associate a difference equation, right? So if you take S, we take a section of the bundle, and of E, we can act on the section with A, or we can do the Q shift. And you can ask what is the space of solutions of this difference equation. So in fact, if you hear a physicist talk about Opers, that's what they usually do. Like they would immediately start off with this equation, but I'll explain you the geometry behind it. Okay, now, so first, what is a connection? A meromorphic GLN Q connection over P1 is a pair of the bundle in this linear map A, where E is trivializable, rank n over n over P1, and A is the, well, it's basically section of this sheaf, right? So we have, structure sheaf over P1 is basically, it's a fancy way to say it's a space of functions from E to EQ, right? So for which A of Z is invertible. So it lies in GLN, and you can similarly introduce the SLN version if you require that the determinant is equal to is equal to 1. Okay. Any questions? Yeah, please go ahead. What's that? Okay, ask me later if it's there. Okay, so and now what is Oper? So here's the condition. So the GL2 and yes, for this for now on, let's consider example GL2 or SL2 for this next part of the talk, and then I'll generalize. So because here a formula very explicit. So a GL2 Oper, GL2 comma Q Oper on P1 is a triple of the bundle, connection, and the sub bundle, right? Where this is the E comma A is the Q connection, and L is the line sub bundle, such that the induced map, right, from L into E mod LQ, right? So from the sub bundle into this factor bundle, if you think of it just as a vector space, is an isomorphism. And again, if you have a SL2 Oper, you can define SL2 Oper if you use a SL2 connection instead of a GL2 connection. Now, how this? So first of all, what does this condition mean, and how to write it down? So let's pick a trivialization. So say S is a section of bundle E, right? Now, how can we define this isomorphism? So okay, no, not E. So if S is from L, right? So if S is let section S generates subbundle L, right? And then we can do two things with S, as we discussed before. We can make a Q shift, or we can act on this with the with matrix AZ. Now, this condition here tells us that these two vectors are not linearly independent, right? So if you take a vector, you act on this with a linear transformation, right? So it usually, unless it's a degenerate transformation, the vector rotates around, right? And maybe stretches if it's GLN, and then it's no longer collinear with the vector that we had before, right? So and there's also Q shift. So basically, that's what it says, right? So that the as we act on the vector in L, right, then it moves us away from that subspace, from that sub bundle. So that's what SL2 Oper does. Okay, now we need to upgrade the definition a little bit because we need some more structure, right? So we can it's perfectly fine to work with Opers like this, but for us it won't be enough. So then SL2Q Oper with regular singularities at points Z1 through ZL, which are in this case distinct from 0 and infinity, and then additionally with weights K1 through KL, right? So these are meromorphic SL2Q Oper from the previous definition, but then we allow this isomorphism A bar to fail at some points, right? So we allow it to fail at all those Z's, Z1 through ZL, and also at Z's multiplied by Q to some power. So basically, if index of point Z1 is K1, which means that we can have it fail at Z1, QZ1, Q2, Q squared, Z1, and so on and so forth. So basically, for every point, there's a tower. There's a tower of points. So you can think of it as a cylinder. So there's a C star action around the cylinder, where the right-hand side is actually equal to 0. Okay, and then this Oper is called Z twisted, right? And if there's a gauge, if this connection matrix A of Z is gauge equivalent to a diagonal matrix Z, which lies in the center, right? So it lies in the center of the cartan of the well, yeah, it's just it lies in the maximal torus of group G of Z.
So it seems like K's are constrained to be integers.
Yeah, K's are integers. That's right. So these are weights. Yeah, that's right. And then they will become like in the differential version, they'll be just spins or whatever. Okay, now to do calculations, we need to have one more part of definition, which is called Miura q-Opers. So again, the word Miura appeared in Gayota's talk yesterday. It's not unrelated to what I'm going to tell you, but it's not immediate either. So Miura SL2 q-Oper is a quadruple. So now we have, so we have bundle, connection, subbundle, and then there's a second subbundle L hat, where this thing is an SL2 Oper from the previous page, and L prime is another line subbundle, which is preserved by the Q connection, right? So it's an invariant subspace. So again, let's give an example. So we choose a trivialization L for L, and then I parameterize the components of the section as Q plus and Q minus, and then let the twist element from Z twistedness condition be equal to the diagonal matrix with a zeta and zeta inverse, right? And then you can see that this condition here, this q-Oper condition, it's a determinant of a 2x2 matrix, right? So it's Q plus of QZ, Q minus of QZ, zeta. So if A is equal to Z, if it's a diagonal matrix, then the second vector looks like this, right? You compute determinant of this 2x2 matrix, and you get you'll get this expression, right? So which looks exactly like the left-hand side of the QQ system, and on the right, instead of 0, we have polynomial lambda, which contains all the information about the singularities, right? So we have those ZPs are, well, the singularities, and then you can also add those towers of singularities.
I have a question.
Yeah.
So do we get the connection to the 3D theory through this QQ system because it's equivalent to beta equations?
Yeah. So exactly. So yeah, right. So first of all, as Sabek was saying, you can derive from this. You can derive beta equations. Second of all, these are more generic than those you get in 3D n equals 4 theory, because in 3D n equals 4 theory, so if you take Grassmannian square, if you take Grassmannian, then n must be greater or equal than k. However, like here it's not true anymore. So n would be, so this will be somehow related to n, right? This degree, and the degrees of q plus. So here in this calculation, degree of q plus is equal to little m, right? And then so that little m would be this k here, right? And that thing would be equal to n. So there are some inequalities on these numbers. There are no such in three-dimensional theory, in the 3D equals 4 theory. There is no such thing in Opers. So in that sense, it provides a generalization. So it's a much bigger space. So space of Opers is much bigger than the K theory of the Q varieties, right? With given framing. It has like
the integer K's, the weights, do they determine the spins of the spin chain?
Yeah, that is true. That is true. Yeah. So if you look here at the formula here, so see those R's, RP is some combination of those K's. Yeah. So like in the this is the left-hand side, right? It's kind of the monodromy part. Yeah. So spins appear here, and they depend on K's. Yes.
I see. Thank you.
Other questions? Yeah. Now this is sort of here. The slide illustrates the trick. So if you have and then also notice that the dependence on the auxiliary polynomial q minus has disappeared. So there are two polynomials, q plus and q minus, but then you can eliminate by evaluating left-hand side and right-hand side at the roots of q plus and shifted roots of q plus. You can completely eliminate the second polynomial. So does not play a role does not appear in the beta equation. Now, so that is because of this Miura condition in a sense. So in a sense, we only need 1/2 of the components of the section in order to write down the equation. And then, of course, you can ask us, can we switch them? Can we swap them around? Yeah, the answer is yes. That would correspond to what is called Beckeland type transformation that would switch off q plus and q minus. So for SL2, it's kind of trivial, but for more complicated root systems, it's actually very non-trivial, and we use it a lot to prove things for general case.
I have another question about this relation to the x-axis pinching.
Yeah.
Does it have twisted boundary condition, twisted periodicity? Is it
twists are so zeta. So the z. So these are the twists.
And zeta was in the q-Oper side. What was it?
You mean which q? So
in the q-Oper side, the zeta was.
So there's a gauge transformation that diagonalizes the q connection.
Mm-hmm.
Yeah, that's right. Okay, so I don't have much time left. So okay, let me formulate at least a statement for SL2. And now, so then you can do the q-Miura transformation. So for Miura-Oper, because of that invariant subspace condition, the matrix A is always upper triangular like this, right? And then you can find explicit gauge transformation V, which diagonalizes the Oper, right? So it reduces it to the diagonal matrix. And then in Miura case, you can not only find this V, which takes values in G of Z, right? In the loop group, right? G of Z, but it actually can live in B plus of Z, right? In positive Borel. So B plus versus B minus is the same choice as Q plus versus Q minus, but yeah, so Miura-Oper is diagonalized by elements from Borel, right? Which is a stronger condition. Okay, and then here you would do the following. So you take basically what you can identify explicitly this gauge transformation. Again, see it's an upper triangular matrix. So and so too it lives in the positive Borel, right? And then you can also write down what the polynomial lambda, the singularities of the Oper means in terms of components of this transformation. So the q-Oper condition, this one, is equivalent to the SL2 QQ system. Yeah, so kind of it's a generalization of quantum classical duality. And then if you think about difference equations, then well, you can take, so here's the difference equation that is associated to this Oper. Because Oper is upper triangular here, you can in this two-component vector S, you can eliminate second component or the first component in the favor of the second one, and you can write down the second order difference equation like that. Okay, and then finally, let me show you how this construction actually generalizes the TRS Hamiltonians. So take Q minus and Q plus of the simplest possible form. Well, maybe the simplest will be constants, but yeah, let's take next simplest possible form. So if Q plus is a polynomial of degree 1 and Q minus is monic polynomial of degree 1, you can only make one of them monic by gauge transformations. And then you will write down the Oper condition for those things, right? So if S of Z, if the section of subbundle L is this vector, you write down the Oper condition. So I remind you, it will be this. And then assuming that the Q connection has been already diagonalized, so this is equal to this polynomial lambda here, right? Then this Oper condition is equivalent to this equation. So it's a quadratic equation, right, in Z. So in our description, Z is the coordinate on CP1 on the base, and its coefficients are nothing but trigonometric, like Simon's Hamiltonians, right? So where the coordinates of TRS system are played by twists, right? Momenta are roots of q plus and q minus. And yeah, and then, well, so, and then there are two singularities here, z plus and z minus. So the q-Oper condition itself is literally the spectral curve of the TRS model. And that happens for the simplest possible choice of q plus and q minus. Now you can imagine what happens if you take higher degree polynomials, so it will be something more general. So the upshot of this first part of the story is that, yes, you can generalize it, quantum classical duality, and it leads you to very interesting geometric structures in quantum Q-Lang lengths. Okay, I think I should stop because yeah, I started 10 minutes late, but I don't want to kind of overload people with the information. Good, thanks. Do you guys have any questions? When I have more to say, but I think I should stop.
But would it be possible to uplift this correspondence even for the quantum TRS?
I mean, like, yeah, in a sense, like, yeah, okay. So say I have my right, so I have some more complicated Oper, right, and which looks like some deformed TRS, right, and ask what's the spectrum. Yeah, totally, sure. Yeah, I don't think it has been done. Like, you know, in this case, like I said, so it loses connection to geometry once you go beyond this kind of framework. And yeah, it's interesting if there's some formal solution of those different separators would exist. Yeah, it's a good question. Yeah, I don't know. It hasn't been studied. Yeah, sounds like an interesting project for a PhD student. Yeah. Okay. So yeah, basically good. And yeah, the story goes on. Like, for example, we can talk about quantum Wronskians. There's a you can think about Opers in terms of this quantum Wronskians, but yeah, so we should get the paper about ODIM very soon, so I'll be able to you know, stay posted. Okay, other questions? Okay, so yeah, we can move to Sasha. Hi. So can you try to share your screen? Share your screen.
Okay. Is it okay?
Yeah. Okay, good. So great. So let's go. So our next speaker is Alexander Gorsky from IITP Moscow, and he'll be talking about dualities in integrable many-body systems and integrable probabilities.
Okay, so thanks for invitation to give a talk. It's such terrible time, actually, I condemn the Russian aggression and support the people of Ukraine. And my talk is devoted to the interplay between two seemingly different issues. First, one of them, to some extent, is described by Peters in previous talk, namely dualities in integrable many-body systems. And there is another big piece of science, it's so-called integrable probabilities. And it turns out that there are some mysterious relation between different observables in integral probabilities, and I'll argue that these mysteries are just the manifestation of dualities in the integrable many-body systems. That's the aim of my talk, and the subject of my talk is based on paper with Mikhail Vasilyev and Andrei Zotov in arXiv and some work in progress. Okay, so the plan of my talks is as follows. So I'll describe provides some motivation for dualities and remind some well-known facts concerning the Kalogero-Rusinov family and spin chain family. Then I remind two dualities which are familiar in the world of integrable systems. First, I'll consider so-called spectral duality, which acts and interchange different many-body systems within families, and then turn to so-called quantum classical duality mentioned in the previous talk, and its generalization, quantum-quantum duality between families. And just quantum-quantum duality will be relevant for the integrable probabilities. Then in some, I'll discuss in some detail the example, to some extent new example, actually new example of which relate the so-called TASEP system, totally asymmetric system. And on the other hand, there is the degeneration, some limit of Rusinov system, so-called goldfish model. And also, I mentioned some interplay for the system and QKZ. Let me start with some general warm-up slide. So let me remind that Kalogero system is the system of n particles with some interaction. And in what follows, I'll restrict myself by rational and trigonometric cases, although the title of the workshop is Elliptic workshop. I will consider the elliptic situation, since there is no elliptic version of probabilities at the moment. So I'll restrict ourselves by trigonometric case. Kalogero system is very familiar, and just mentioned a few examples. It describes the quantum Hall effect, particles near black hole horizon, dynamics of defects in super-Young Mills theory, or some topological degrees of freedom in two-dimensional Young-Mills theory, if you consider the heavy charge. As Peter told in the previous talk, it is a system whose phase space has a group origin, and we start with some very simple phase space manifold, which is typically cotangent bundle to some algebra, or cotangent bundle to group, or Heisenberg double, or something like this. Impose the moment map for coadjoint action on this manifold, and select the peculiar value of the moment map, the operator O here. Then there is a commuting set of Hamiltonians, and Lux operator is the solution to the moment map equation if we assume that Q is the diagonal element. So this is just the restricted motion on the group-like manifold. Another family which I will consider later, it is Rusinov-Snyder system. It is a relativistic generalization of Kalogero. And the simplest Hamiltonian is written here for the hyperbolic version and for rational version of Rusinov-Snyder system. It has two interesting limits. One of them is very familiar. It corresponds to parameter C tends to infinity with eta fixed. It provides in the limit the conventional Kalogero system. A less known limit corresponds to fixed speed of line, but coupling constant tends to infinity. It is so-called goldfish model invented by Kalogero a long time ago. And similar to Kalogero system, we could write down the Lux operator for this model, Lux equation, and the corresponding equation for the velocities, which will be useful to comparison to Bertrand-Zatz equation. Similar to Kalogero-Moser system, it's very useful object, Roisner-Snyder system. It describes the N-soliton system in Sine-Gordon theory, dynamics in defects not in 4 dimensions, but in 5-dimensional situation. And also it provides the dynamics on the modular space of flat connection of the puncture torus. Oh, this is very universal system. This is one side of the duality system, and another side, which I'll consider later, involves different spin chains. Let me start with x-axis spin chain and its degeneration to Godin model. So we start, for instance, when we consider Lux operator for the spin chain with the proper Poisson brackets and Poisson brackets for the local Lux operators, which involves the corresponding R matrix. What is important, we consider them local, non-local commuting Hamiltonians. So when we consider the limit of inhomogeneous spin chain, here we see that the spin chain is inhomogeneous and parameters are zk here. We have non-local Hamiltonians are just residues of the first order in the trace lex squared operator. And the corresponding non-local commuting Hamiltonian looks as follows, where lambda is the matrix providing the boundary condition, and zi as the inhomogeneous in the initial space chain. So you see that generically the Godin model has 2 sets of parameters, inhomogeneities and eigenvalues of the twist matrix lambda. To consider, if we consider the Monotreme matrix representation, we just start with transfer matrix. As I told above, introduce this twist matrix and inhomogeneities, and the limit from trigonometric from xxz inhomogeneous model correspond to eta equals to 0 with additional rescaling of twists. So these are well-known facts, and what is important for me is that there are 2 sets of parameters, twists and inhomogeneities, and there are non-local Hamiltonians. So let me turn to the first example of duality to describe this duality. Let me consider 2 simplest examples. So let us consider some Hamiltonian system and consider energy level of Hamiltonian system on the phase space. P and X are coordinates on the phase space. And when we have levels of energy levels of Hamiltonians, it's possible to consider the standard Hamiltonian evolution at the fixed energy level, as well as more non-trivial evolution across the energy levels. And in fact, these are just 2 dual systems. One system provides the Hamiltonian evolution along the energy level, and the second system correspond to evolution across the energy levels. What is important is that both of them have the same wave function, and however, in that wave function, the coordinates and energy parameters get interchanged. The spectral duality in the Kalogero-Moser-Ruizinars family has been introduced by Ruizinars, and it maps with, in this sense, a rational Kalogero-Moser system is self-dual. In this case, action and coordinates variables and symmetrically. And as have mentioned in the previous talk, trigonometric Kalogero-Moser system is spectrally dual to rational Ruizinars-Schneider model. As I have mentioned, when you consider the quantum spectral duality, the Hamiltonian, Kalogero-Moser Hamiltonian acts on the coordinates, and energy depends on variable k. And on the other hand, when you consider the same wave function and acts by the Ruizinars-Schneider Hamiltonian on this wave function, but now on parameter k, and instead of differential operator, we consider this difference operator, and energy depends on coordinates in the previous model. So both of them have the same wave function, and this is essentially important. Similarly, there is the same spectral duality on the spin chain side. Actually, it was invented by Harnad, Adams, and Urtubis approximately at the same time as was done by Ruizinars for Kalogero-Moser system. In the language of Lex operators, the spectral duality for inhomogeneous spin chains is based on the very simple determinant identity. So we consider determinant of n over large n over n matrices for one system. L is operator for spin chain, and on the other hand, there is the dual system when Lex operator has different dimension. However, this identity holds, and in the same language, the rational Godin model is self-dual, and on the other hand, the trigonometric Godin model is dual to XXX spin chain. XXZ spin chain is self-dual. So this is a classical relation. We know that determinant of Lex operator characteristic polynomial of the Lex operators provides the spectral curves, that is generating function for the conserved quantities. How it works at the quantum level. So instead of the conventional Schrödinger equation for Kalogero-Moser system, here we consider the quantum level, the so-called the Knizhnik-Zamolodchik equation, which plays a similar role here. And the corresponding Hamiltonian, the quantum level, can be derived from quantum Monotreme metrics. And the duality between pairs of Knizhnik-Zamolodchikov and more generically quantum Knizhnik-Zamolodchikov equation was developed in many papers by Mukhin, Tarasov, and Farchenko. And there is a quite complete classification for the pairs of Knizhnik-Zamolodchikov and quantum Knizhnik-Zamolodchikov system. Some different terminology sometimes is used, and sometimes one of this dual equation is so-called dynamical Knizhnik-Zamolodchikov equation. And one operator in Knizhnik-Zamolodchikov equation in one system acts on the inhomogeneities, and the dual Knizhnik-Zamolodchikov equation operator acts on the twists. And as I have mentioned, the twist and inhomogeneities get interchanged in the spectral duality. Let me turn to the second type of duality, which is important for me. It is quantum classical duality. Once again, let me start with the toy picture. once again consider some Hamiltonian system with 1 degree of freedom and consider energy levels. And let us consider the intersection of 2 Lagrangian submanifolds. So one submanifold is the fixed energy level, E2 or E1, and the second Lagrangian submanifold is fixed coordinate here. And it turns out that when we consider the intersection of 2 Lagrangian manifolds, here in this toy picture, just 2 points, these points turns out to be the solution to Berkeley equation in auxiliary spin system. So this is a simplified one model, but generically we have many body system, and nevertheless we have similar intersection of 2 Lagrangian submanifolds. The one submanifold correspond to selection of Hamiltonian, and the second fixing of coordinates. The quantum classical duality mixes, interchanges the one system from classical Kalogera-Moser or Rosenberg-Snyder type, and on the other hand, there is quantum Godin or quantum XXX or quantum XXZ model. And identification of parameters is as follows. So the Planck constant quantum parameter at the spin chain sides correspond to the coupling constant in Kalogera-Moser or Rosenberg-Snyder system. Inhomogeneities at spin chain side correspond to coordinates in Kalogera-Moser system, and local Hamiltonians at spin chains correspond to momenta of in the Kalogera-Moser system. The twists its spin chain correspond to Hamiltonians at Kalogera-Moser side. So let me summarize the duality at the quantum classical level. Berkeley's equation at spin chain correspond to intersection of 2 Lagrangian manifolds. And these 2 Lagrangian manifolds correspond to fixed coordinates. Fixed coordinates at Kalogera-Moser side correspond to fixed homogenities, and fixed Hamiltonians at spin chain at Kalogera-Moser side correspond to fixed twists. Berkeley's equation just the equation for classical momenta. However, this duality can be generalized, and just this generalization will be the most important for me when I'll consider the relation with quantum probability. We introduced the Planck constant at the Kalogera-Moser side, and the question is, what is the counterpart of the quantum Kalogera-Moser or quantum Rosenberg-Snyder model at the spin chain side? It turns out that that the corresponding duality relates the wave function of Kalogera-Moser or Rosenberg-Snyder model and solution to the Kniznik-Zamolodchikov or quantum Kniznik-Zamolodchikov at the spin chain side, supplemented by the additional Matsui-Cherednik projection. So the procedure is as follows. So we solve the Schrödinger equation at Kalogera-Moser side and compare it with the solution to the Kniznik-Zamolodchikov equation. As example, I present here the Kniznik-Zamolodchikov equation for the simplest rational case. And what the most important point is the parameter in Kniznik-Zamolodchikov parameter in Kniznik-Zamolodchikov equation is just the Planck constant in Kalogyra-Moser side. So we have two Planck constant, and they have different roles. The Planck constant at the spin chain side provides the coupling constant in Kalogyra system, while on the other hand, the Planck constant in Kalogyra-Moser system amounts to the Kniznik-Zamolodchik equation. As I have mentioned, to have complete relation between object at Kalogyra-Moser spin chain side, it's necessary to impose the so-called Natsui-Cherednik projection. To some extent, informally, we consider the solution to Kniznik-Zamolodchik equation in one variable and consider and impose some symmetrization with respect to all variables. Since these variables are or inhomogeneities or twists, so we should look at the symmetrization of Kniznik-Zamolodchikov or dual Kniznik-Zamolodchikov equation with respect to inhomogeneities or with respect to twists. If we consider that semi-classical limit, that is Planck constant tends to infinity, it's possible to obtain the Bertrand-Zatz equation. Bertrand-Zatz equation appear in the semi-classical limit of Kniznik-Zamolodchikov equation. So there is a clear-cut relation between semi-classical limit of quantum duality and quantum classical duality. This is just the semi-classical limit and nothing else. One more important point is that so far I discussed two types of dualities. One spectral duality, and the second the quantum classical and quantum duality. And the natural question is whether these two types of dualities are consistent with each other. And indeed, it can be shown very explicitly that at the classical limit, we can consider the following commutative diagram, which relate the spin, two pairs of spin chain models and two pairs of many body system, and the same in a similar manner. There is quantum consistency of two dualities. One duality relates the pairs of Kniznik-Zamolodchikov equation, two dual Kniznik-Zamolodchikov or quantum Kniznik-Zamolodchikov, and on the other hand, interplay between two wave function of many body systems. Okay, so before turning to integrable probabilities, let me also mention that this quantum classical and quantum duality can be seen by in geometrical setting. It was argued by Nekrasov-Shetashvili that Bertrand-Zatz equation at spin chain side provides a cohomologies of or co-theory on some manifolds. And since we have a duality, we could expect that the Kalogyra and Rosener system also are related with cohomologies of co-theory on some manifold. And indeed, it's true. Very long, very old paper by Giventhal and Giventhal-Kim shows that that open to the chain is related to homologies or to flat manifold, and more recent development of this issue shows that Kalogyra system and Rosener system are related to Katanen bundle to flat manifolds. Actually, as was Egid told before, the spectral duality has a very simple interpretation in terms of branes. It was just 90-angle rotation of the brane diagram. It is the spectral duality. And on the other hand, as Peter discussed before, the quantum and quantum classical duality is just the realization of Hanani-Witten move for the quiver brain configuration for the quiver gauge theory. So there is a clear duality issues. Two types of dualities. Everything is clear, at least at the trigonometric level. So let's turn to the second part. So the second part of the title. This is the so-called integrable probabilities. So it is just mathematical stuff to some extent, and here I'll try to argue that this mathematical story meets with the theory of integrable system. So let me say a few words about the general landscape of integrable probabilities. There is so-called at the top. There is one family of which has McDonald process with two parameters at the top. It can be reduced to q-Tucker generic LMT model, whole Little process. So one considers that some probabilistic model, and the particular example depends on the number of parameters. The most simple one is the so-called Schur process. From the conventional quantum mechanics, okay, so I will turn later to the linking of quantum integrable system and some object from integrable probabilities. Let me say a few words about the logic to some extent. When there are three standard objects in integrable probabilities. The simplest one is the function of some section depends on lambda. Typically, it's parameterized by some partitions, and variable y, which in this language is termed as specialization. From the viewpoint of quantum mechanics, it is a kind of just wave function. More complicated object is so-called measure, which is the product of two probabilities with the same partitions, but with different specializations. Being translated to the language of quantum mechanics, it is related to Laplace transform of Wigner function. Both of them are related to more or less familiar object in quantum mechanics. However, there is also the so-called process introduced by Kunkov and Reshetikhin, and it is less familiar. It is the product of function with different specialization, and the partitions obey so-called interlacing condition. So we see there is embedding of the corresponding partitions for the corresponding function. So the question is there standard? Okay, so in what follows, I'll argue that this object and the object, namely probability and measure, and some relation between probabilities as measured are related to the dualities I discussed before. Okay, what kind of dualities in probability for integrable probability are relevant? There are some just observation for people working in integrable probabilities that there are some identities between observables if we consider observable with respect to McDonald measure, and on the other hand, the observable with respect to higher rank stochastic sixth-Vertex model. And the arguments of McDonald measure were identified as the local jumps in sixth-Vertex model. And there are some unclear derivation of non-symmetric McDonald polynomial in terms of partition function of sixth-Vertex model. Twist with on the cylinder with the twist. There were no rational explanation of this observation. How the relation looks like? So we consider expectation values of different complicated observables. One of them on the sixth-Vertex model, and the second on the with the McDonald measure. And the expression are quite complicated. There are multiple integrals. And nevertheless, different multiple integrals with different rotations of contours are the same. This issue has been developed by a series of papers, Borodin, Petrov, Corwin, Buffet, and Orr. And another example, some limit of the same story is we consider some degeneration of sixth-Vertex model, so-called q-Opers, and consider some observable, consider expectation value, and on the other hand, consider the generation of McDonald measure and evaluate some another stuff on with the McDonald measure, and once again we have relation between two seemingly different objects. Let me comment that these variables here, this is the operator, which is the limit of McDonald operator, and some Gelfand-Settling scheme is involved in this picture. Let me consider a more specific example. So this is the observation which has been done by in the world of integral probability. Let me explain how it works how it can be identified as the quantum duality. I'll focus at the most simple case suitable for explanation. Okay, so at the one side of the dual pair, we consider inhomogeneous Tassip stochastic model. So Tassip model is just the system of particles when particles can move to the free places, and when you consider totally symmetric means that that the particle could jump only in one direction, here to the right. And inhomogeneous means that jumps are position dependent. So the probability of jump here and probability of jump here are different. And also in what follows, I'll consider not the simplest Tassip model, but so-called higher spin or higher rank or higher species, different names for the same So it means that these particles have additional quantum number, which belongs to some representation of say, for SUN, and jumping parameters generically depends on the group index. What is the most important that these stochastic models can be interpreted as the Markov dynamics. When we consider homogeneous situation, the Markov process looks as follows. So we consider the probability of be a kind of Hamiltonian Schrödinger equation, where Hamiltonian can be related to the XXZ spin chain Hamiltonian. It is for homogeneous case, but let me know that we are interested in homogeneous case when the jumps are position dependent. The transfer matrix for inhomogeneous case looks as follows, where R matrices here are, I'll show in the next slide. And what is important in this case, instead of evolution with respect to Hamiltonian, the operator which provides the evolution is built from the transfer matrix. So we consider the following combination of transfer matrix, and the discrete time evolution can be governed by the corresponding effective Hamiltonian. And we will be interested in the analog of, it's not exactly the so-called steady state, but it's analog of steady state for inhomogeneous stochastic models. For the inhomogeneous TASIP, which is for us, the R matrix is quite simple. So we can write down it in the following form. And however, there are some specifics when we consider the R matrix analysis of a stochastic model. It is related to so-called unitarity constraint. Since we are dealing with probability, it's necessary to keep the normalization and or in other terms, unitarity of evolution. And this unitarity constraint can be reformulated in terms of this additional equation. The corresponding steady states can be for the TASIP model can be expressed in terms of operators which belongs to Faddeev-Zamolodchikov algebra. There is so-called Faddeev-Zamolodchikov algebra of vertex operators intertwined by R matrices, and here the corresponding R matrices is written here. So let me formulate how this duality looks like. So when you consider TASIP model with stochastic model with these inhomogeneity parameters, then it turns out that these inhomogeneity parameters in TASIP model can be identified with the rational Kalodgera goldfish model. That is the peculiar limit of Ruizinar's model. The velocities are in the Kalodgera goldfish model are related to local Hamiltonians in the corresponding TASIP or 5 vertex side of the story. And sorry, and the conserved quantities can be related to twists in the corresponding TASIP model. The variables V here correspond to twists with particular multiplicities. The same can be done for the trigonometric case. So we could consider trigonometric goldfish model. And that is, at the previous slide, I consider the limit of rational Rosenar's model system. And here I consider the limit of trigonometric Rosenar's Snyder model, the same one, and so-called trigonometric Tassip case. Once again, I consider inhomogeneous stochastic model with higher ranks. And one and the same, there is identification of local jumps in Tassip model and coordinates in Kalogera-Moser system, Kalogera-Goldfish model, and similar the dot-ansatz equation at the Tassip side are related to derivation of momenta of particles at goldfish sites. This is the quantum classical duality, but actually this duality has not been discussed at all in integrable probabilities. And let me turn to the quantum duality. And indeed, in this case, we could consider link with the relation observed in integrable probabilities. So how it looks like. We consider sorry. We consider kind of Knižník-Zamolodchik equation where the corresponding operator it is Q Knižník-Zamolodchik equation, and psi is a solution, and operator K depends on R matrices, and R matrices depends on the local inhomogeneities, and inhomogeneities in the stochastic story means the local jumps. And there is also, so these are sets of operators. This is a difference operator acting on the corresponding ice variables. H is the Planck constant, and R is the R matrix, which I have discussed before. And also there are parameters of the corresponding twists. So this is the Knižník-Zamolodchikov, and here the quantum Knižník-Zamolodchikov equation. However, if I consider the action of a rational Rosenar's model acting on the overlap of a solution to Knižník-Zamolodchik equation with a peculiar vector discussed before, and then it turns out that this overlap is just the eigenfunction. I remind that psi is a solution to quantum Knižník-Zamolodchikov. Omega is peculiar vector, which provides the Matsui-Cherednik projection. And if we act by goldfish Hamiltonians, non-local, the set of goldfish Hamiltonians HK on this object, we get the we see that this is eigenfunction of the goldfish Hamiltonian with the eigenvalues expressed in terms of twists at the spin chain side. So let me repeat. We start to formulate the quantum goldfish duality. We consider the quantum книжных замолотчиков at Tasep type, acting on the variables which fits the local jumps. Consider the interplay, the overlap of the solution with specific vector, and we get the eigenvalue equation for the goldfish Hamiltonian. This is for rational case. Also, we consider it's possible to consider the similar quantum duality for between the trigonometric goldfish model and trigonometric version of inhomogeneous Tasip. So we consider trigonometric version of KKZ. The corresponding operators are once again expressed in terms of R matrices, which depends on local jumps. Let me remind that the I's are the local jumps. The special vector I talked about is expressed here. We consider the action consider the overlap of the solution to the Knižnik Molotchikov with this vector acts by the trigonometric goldfish Hamiltonian and get corresponding eigenvalue, which is expressed in terms of twists in the Tasip type. Let me reiterate that we consider non-homogeneous twisted higher spin Tasip model, and it is dual to the quantum goldfish model. Let me, before turning to my conclusion, let me consider some limit. It is known that it was argued by Ruiz and Ars a long time ago that goldfish limit of trigonometric Ruiz-Snyder model is dual in the spectral sense with open topspin chain. And the question is whether this duality is consistent with the quantization picture. And to this aim, it's possible to consider to write down the version of Knižnik-Molotchikov equation for which are relevant for Toda. It is just peculiar limit of quantum Knižnik-Molotchikov equation. In this limit, the following operator are relevant. It is so-called Nil-Heke algebra with operators Ti's and Yi's with the following commutation relation. And it turns out that just this operator is relevant for the proper limit of Knižnik-Molotchikov equation. And indeed, we see that if we consider and perform the same procedure, consider solution to this equation at the Matsuo-Cherednik projection, and it turns out that this solution upon Matsuo-Cherednik projection provides the open Toda chain wave function of open Toda chain. Therefore, we see that the limit of I considered before in stochastic side is consistent with the spectral duality for goldfish model. So before completing, let me say a few general comments. I have mentioned two types of dualities. Spectral duality in the stringy world version can be related to mirror symmetry, and on the other hand, the quantum classical and quantum duality is nothing but the three-dimensional mirror symmetry, so-called. Before I considered only trigonometric cases. Some dualities are known for elliptic cases as well. However, there is no developed elliptic version of integrable probabilities. It could be a very interesting issue to develop the elliptic version of probability. However, there are some deep questions concerning the probabilistic interpretation. And also I have mentioned a relation with Superionak-Mills theory, but to some extent Peter missed this point in the previous talk. Therefore, my conclusion is as follows. So we have explained the mysterious dualities between two families. So there are some mysterious identities, and these identities turns out just the manifestation of quantum dualities for integrable multi-body systems. There is very interesting question concerning the interpretation of stochastic process. So far, we interpreted the dualities for probabilities and for measures. However, there is an open question under consideration how the process, which is unusual object from the quantum mechanical viewpoint, how it can be generalized at the integrable side. And just as application of our stuff, we consider we derive new duality between limit of goldfish limit of Rutgers model and periodic and homogeneous high rank Tassip model. So thank you for your attention.
Thank you, Sasha, for the talk. Very broad view and actually a new direction mentioned by probabilities. Are there any questions, please? Maybe some comments, additions. So maybe I will ask just about these double elliptic systems. You did not comment at all, just mentioned that it doesn't work. But somehow, can you express your opinion about this recent progress, where it has stuck at this time? Because there was some progress recently, and what's the current situation?
Well, the current situation is so there are some well, okay, so. As a classical two questions, so you could consider this system as a classical limit or at the quantum level. At the quantum level, there is some progress of relation to wave function, if you wish, of this system to so-called QT generalization of Kniznik-Zabolochko equation. And it turns out that there is a relation between QT generalization of and representation of dim algebra. So there is some algebraic progress concerning the embedding of this del system into the dim algebra. Concerning the dualities, there are some observation I have mentioned. The persons who are involved in this stuff, and there are several papers which provides some different representation of Hamiltonians of del systems, double elliptic system, lowest Hamiltonian. So complete derivation of all Hamiltonians, to my mind, is still lacking. And also, there was our paper with Shamil, Peter, and Alessia, where we have tried to consider the Inozemtsev limit. Typically, we consider, when we consider elliptic model, we could derive some, for instance, from elliptic algebra, we can get the periodic Toda. From elliptic resonance, we can get periodic relativistic Toda. However, from double elliptic system, it's the analog of Inozemtsev limit is more complicated, and there are some examples for the lowest Hamiltonians, but also there is some question how to get the analog of double elliptic Toda system, if you wish. So this is there are some steps in this direction, but certainly this problem hasn't been completed yet.
Okay, thank you. Are there more questions? If not, then Sasha, please stop sharing your screen. So now it's my turn to give a talk. Okay. Is this one? Yes. Do you see the screen? Do you see the screen? I don't hear anything. Do you see?
Yes.
Okay, now I hear. Okay, so probably I will start. Hello to everybody. First, I would like to thank Peter for organizing this workshop. I'm just auxiliary co-organizer. The initial idea was belonging to him like 1 year ago, and he's maybe not so much experienced in these things. He was asking me advices of certain type, and after some sequential advice, he said, let it, you be also the co-organizer, so I agreed. But the majority of the things were done by him, so I would like to thank him. Okay, the title of my talk you see on the screen, it's about limits of the so-called elliptic hypergeometric equation, and some new limits will be described, and they will be applied to the description of what happens in concern to that in elliptic integrable systems by Rusinars and Van Diezen. Okay, I would like to start from an elliptic analog of the Euler-Gauss function, which has the following form. So it is integral over unit circle, opposite direction, of the product of 16 elliptic gamma functions in the numerator and 2 elliptic gamma functions in the denominator. And this is just some normalizing infinite product, and the definition of the infinite product is given here. Important thing is that this integral, parameters of this integral should satisfy the so-called balancing condition. The product of t's must be equal to pq squared, and some additional constraint in order to have this contour exactly the unit circle. And you saw already many times the definition of elliptic gamma functions, and satisfies first of the difference equations of this type, where theta is just the shortened theta function. Also, you saw many times this function. And I introduced this function in the process of investigating the symmetries of elliptic hypergeometric integrals. And the simplest hypergeometric integral emerges from this function when you set two parameters equal to the product of two parameters must be equal to pq, and then it simplifies. For instance, if t7 times t8 is equal to pq, then these parameters drop out completely from this function, and it becomes now computable explicitly. So here is the result. It is called the elliptic beta integral, and then this function is expressed, this integral is equal to the triangular product of elliptic gamma functions of the described form. And actually, you saw elliptic hypergeometric integrals many times in the talk by Shlomo Razamat, and here this result goes to 2000. It actually, I conjectured this formula just on the turn of millennium. And it's the very first, actually, this is the introduction of this class of special functions, transcendental elliptic hypergeometric functions. And just to mention that it is done 5 years before the notion of superconformal index was introduced, and 8 years before Dolan and Osborne have identified this class of elliptic hypergeometric integrals with the superconformal indices. So it's rather old now result. Now I jump to the elliptic hypergeometric equation. In the proof of the elliptic beta integral formula evaluation, I used the contiguous relations as auxiliary tool, and that was very helpful for proving the theorem. And as I said, this V function was introduced from the analysis of the symmetries of elliptic hypergeometric integrals. And when you combine these two objects, the contiguous relation and symmetry transformations, then you get a lot of the C of contiguous relations. And one of them has the form of the q-difference equation of the second order, which is exactly the elliptic hypergeometric equation. Here is the description. So first, I introduced the following combination of V function. You divided by 4 elliptic gamma functions with such particular choice of the parameters. And then this function satisfies this linear difference equation of the second order. Here, this expression means that in the variables, in the parameters of this function, I replace T6 by Q T6 and T7 by Q minus T7. Why I do it so? Because of the balancing condition. Remember, this balancing condition forces the product to be fixed. And that's exactly, I have to do, once I scale this, I have to rescale back another parameter, and that's what I'm doing here. Well, and the potential D is cute combination of theta function. It has the following form. You have here 8 theta functions in the numerator and 8 theta functions in the numerator with some particular cute combination of parameters. And this term means that you have exactly the same expression as this one previous, with the parameters T6 and T7 exchanged. And so this is the equation. In order to see that this is a q-difference equation of the second order, you just may parameterize T6 and T7 as given here. And then you see immediately that this change is equivalent to just scaling z to qz, and in this piece it will be scaling of z by q inverse z. And so it's exactly the q-difference equation of the second order. Okay, this was the form of the elliptic hypergeometric equation when you had the solution symmetric. It had S8 symmetry in parameters, but the potential was very asymmetric. You can invert this situation and write the symmetric form of the equation, and as a result get, of course, the asymmetric form of the solution. Here is the result. So the maximal symmetry you can impose on this equation is the S6 symmetry in parameters. So we introduce the parameters epsilon k through some combination of q's, t's, and so on. And then this equation can be written in the following form. And z is exactly the z which emerged, I introduced here through the parameterization of T6 and T7. Evidently now c squared will be T6, T7, and in these new parameters, it will be epsilon 6, epsilon 8 divided by P4. And these parameters epsilon satisfy the following constraints. First, the balancing condition is preserved, it's here, exactly the same one. But what is important, you have additional constraint for between these parameters. Epsilon 8 equals to q times epsilon 7. This is a restriction. So 2 restrictions on the parameters entering this equation. And now how looks the solution? This particular solution, which I started from, it's here. You have V function with some now ugly looking parameterization of the parameters and divided by again 4 elliptic gamma functions. So it's reciprocal to what I described on the previous slide. The symmetry is now hidden, sitting in the equation, not in the solution. You can find general solution of this equation just by, say, permuting parameters, scaling these variables epsilon by p's, because these objects are, these coefficients are elliptic functions of all variables, p's and of z's and epsilons. So therefore, you can scale these parameters entering the solution by these powers of p, even permute the parameters and get new solutions, and 2 of them are independent, and so you can use them as a general solution of the second order difference equation. Okay, that's the key object which I'm discussing during my talk, and now I'm passing to immediately to the generations of this equation and this V function, because it shows what kind of hierarchy of simpler cases are hidden in these objects. And the simplest limit is you take p goes to 0 for fixed q. In order to, here is some formula which explains you how you do it, some limits for the elliptic gamma function, also very easy to see the validity. And you have balancing condition. It doesn't allow you immediately to take this limit p to goes to 0, so you have to clean it. So I scale parameters by powers of p so that the exponents equals to 2, the sum of the exponents alpha, and then the balancing condition for g parameters will be this one. And for instance, in the simple case, when I scale only alpha 7 and alpha 8 set equal to 1, so that only t7 and t8 will be scaled, then in this case, I remove the p dependence using the inversion relation for the elliptic gamma function, and then it's very easy, very trivial to take the limit p goes to 0, and here is the answer. So you have this contour integral of unit circle of now combination of ratio of the infinite products, which is very well known in this theory of q special functions. And in particular, this is the combination of so-called 10 q hypergeometric series, infinite hypergeometric series, and subclass of these functions describes so-called Rahman's q-orthogonal rational functions, and the equation which appears in this setting, the elliptic hypergeometric equation, becomes the difference equation for these Rahman's functions. I will not describe that because it's just a reminder. Now, if you take the further limit q goes to 1 from this trigonometric reduction, then I need the Jackson's q gamma function. It's a ratio of two infinite products times the elementary kinematical factor. And it was proved by Kornwinder and later extended by Reins that the limit when q goes to 1 from this q gamma function to Taylor gamma function is uniform and compacta, and so this result allows you to apply this limit directly in the integrals, and so it's a very nice tool. You get theorems, not conjectures. And applying this now limit q2 goes to 1 to the previous slide function, I will one gets to the fifth function. So first you take p limit, then q goes 1, and you come to the following integral, infinite contour of integration. And here you have now ratio of standard Ariel gamma functions. Some divergent factor is in front of that. That's the asymptotics limit. So that's the limit of the function. And again, I will not describe the equation because it will appear a little bit later. Now, what about the different type of degeneration? So Rusinars came with the following limit asymptotics for the elliptic gamma function, which is described here. When you take all the variables sitting in this integral tj, z integration variable p, q, you can parameterize it exponentially, so that each one has v dependence in the exponent, and take v goes to 0. So all of them go to 1 essentially. And somehow here is the divergent factor, and then the result is coincides with what some people call Fadeev's module logarithm in the theory of special functions, hyperbolic gamma function. And so it's a quite useful function appearing in quantum field theory in many places, and it has the following form. So first you have the exponential of the Bernoulli polynomial of the second order. Here is explicit expression, and gammas without indices is this ratio of infinite products, where q, bold q, is now given by the exponential of ratios of this omega 1, omega 2, which emerge from p and q. And you see, you have here the standard infinite product, which many of you know. And here is the kind of a modular transformed infinite product. You see, q tilde is a modular transform of tau to -1 over tau, the modular transformation used. And you have this infinite product ratio representation, or which is more powerful, the representation, integral representation for this function. And as shown by Rines in 2006, this limit is uniform on compact as well. And so this very powerful result, and it allows you to apply it to, again, the integrals and somehow get from the elliptic hypergeometric integrals everything that goes down in the hierarchy. And here is the result in this case. So this V function again gets some in asymptotics when V goes to 0, gets a divergent multiplier and times convergent integral, which again is the integral over imaginary axis. 16 these hyperbolic gamma functions in the numerator, and 2 this hyperbolic gamma function in the denominator, and some measure. And the balancing condition which existed earlier in terms of T and P and Q now becomes this constraint. So that's the limit, hyperbolic limit. And here I would like now to present how the elliptic hypergeometric equation is reduced. It was obtained by Van de Waal, Rines, and Stockman, following my work, and has the following form. Again, you have now additive notation, not multiplicative as before. So y is the ratio of this E integral, which hyperbolic integral, which I have just described, divided by 4 hyperbolic gamma functions with particular parameterizations, and the coefficient, these potentials, are just very simple reductions of the coefficients we described before. You pass from theta functions to sine functions, and again some cute parameterization dependence on the variables. And again, you see this integral I is symmetric in G variables, and the equation is completely asymmetric, which means that you have actually not one equation, but very huge family of equations obtained from this one by permutation of parameters, and all of them are satisfied by this function. Important point is that this I function is symmetric in omega 1 and omega 2, because that's the property of this gamma 2 function, or this small short gamma function. It's symmetric in omega 1 and omega 2. Therefore, you have not one but 2 equations. At the elliptic level, it was the same, because P and Q symmetry between the norms of the elliptic gamma function allowed you to have the partner of the elliptic hypergeometric equation, just permute P and Q and get the second equation. Very evident. The same is here. So from this equation, you get the second equation just by permuting omega 1 and omega 2. So you actually work not with one equation, but with 2 equations in this sense, plus some permutation in the parameters. But for me, it's important we exactly this fact that omega 1 and omega 2 permutation gives 2, in a sense, independent equations, because further on, I will be breaking the symmetry between omega 1 and omega 2, and we will get different results when I will go further down in the hierarchy of degenerations. Here I will need another result by Simon-Sinars of the limit from this hyperbolic gamma function to the Euler gamma function. An explicit formula is given here. And it corresponds to the case when omega 1 goes to 0 for fixed omega 2. That's exactly how you break the symmetry between omega 1 and omega 2. And up to some simple factor, you get Euler's gamma function. Note that in this limit, you have Q goes to 1, but Q tilde goes to 0. It's important. And because the next one will be different when Q tilde will be again also going to 1. Now, if I should clean to use this limit at the level of integrals and equations, I have to clean again the balancing condition, because omega 1 goes to 0 there is some, you cannot do it there in a straightforward way. So I have to get rid of omega 2 parameter from the balancing condition. So I shift now two parameters by omega 2. Then the balancing condition becomes normalized only to omega 1. Then using this inversion relation for this gamma 2 function, I flipped some gamma functions from the numerator to the denominator. This cleans up completely dependence on omega 2 inside the arguments of these gamma functions. And then it is straightforward to apply this limit after the scaling. I scale gk by pull out the omega 1, which goes to 0, and the remaining I denote as alphas. And here is the result. So this hyperbolic integral diverges and goes to the some another integral, which is rational now. This is the letter R, subscript R. 1, this is 1. It means that this is first rational limit, which I'm describing. Then there will be 2 more. So this integral has the following form. And this is exactly the one which I have described before in the case of when I was degenerating the trigonometric Q hypergeometric integral towards the plane hypergeometric. It's the same. So essentially what I have described 2 different ways of coming to the same plane hypergeometric level, and which I call rational limit number 1. And the integrate the equation, how the equation itself is gets reduced. So I fix for simplicity, for explicitness, this 2 pair I take as T indices 4 and 5, and apply this limiting procedure. It can be done, not so difficult, although requires certain, of course, skill. And here's the equation which results in this sense, in this case. So it's the potential I denote now B of, and again, the same combination as before of the entering objects. And the B function is now a rational function of alphas, again, some cute parameterization. And this function, which emerges as a solution of the equation, is related to the integral which I described before, rational 1 divided by 4 product of 4 standard Euler's gamma functions. So in this limit, this is the limit of the first equation, the first hyperbolic equation, which I described. And the second one was obtained by permuting omega 1 and omega 2. And because of the symmetry is now broken, the second equation yields new relation. It's a highly non-trivial identity, which we didn't see before. I forgot to mention that this is joint work with Gorsky. It was mentioned in this first slide. And here is the point that when I say we, it means Gor and me. So here's the identity which emerges from the second hyperbolic equation. It's now the relation not for one particular function, but the relation between 2 different functions. So the tilde I emerges here, and that tilde I is given by this integral. So you see what's the difference between this and these integrals. For this, I had only 2 gamma functions, the denominator. And here for tilde 1, I have 3. So there is some certain flip of gamma functions. And structurally, it's different object. And somehow I'm curious of what this identity means from the Q special functions point of view, because it's ordinary plane hypergeometric functions of view, because it's, I guess, new and so not known. And we didn't investigate it in detail, just derived. And so this is a rigorous result. Now I'm turning to the main subject of my talk, namely, I described the second rational degeneration behind the elliptic hypergeometric equation. It goes to the so-called complex hypergeometric functions. So here's the standard Euler's beta integral, which can be computed explicitly, very well-known object. And in order to convert this thing to the complexified, to consider the analog of this relation over the field of complex numbers, you take the following 2 parameters, alpha and alpha prime. The difference of these parameters is integer. That's the important thing. Then you introduce the notion that this z square brackets in the power alpha is actually the product of z in the power alpha and z bar, which is complex conjugation in the power of alpha prime. Why I do it so? Because this function is now single valued function of z. That's very important. It's for this quantization is necessary in order to have this factor and have single valuedness. So I introduce the measure. This is standard complex plane integration, and the first beta integral for the complex hypergeometric functions have been defined long time ago by Gelfand, Greif, and Vilenkin in their book. And here is the relation. So integral over a full complex plane of the product of 2 such objects with 2 different parameters alpha and beta. Remember, each of them satisfy this constraint. It can be computed explicitly, and it's given by the ratio of gamma functions times some kinematic factor, which is very simple and has the same structural form. And you see here we have 3 gamma functions in the numerator and 3 gamma functions in the denominator. So at this point, it is convenient to introduce so-called gamma functions over the field of complex numbers, which is given by the ratio of gamma functions, so gamma alpha divided by gamma 1 over minus alpha prime, or if you denote alpha as n plus ix over 2, then this will be 1 plus n minus ix over 2. And this combination you use, then this formula can be simplified, because you see you have here gamma alpha over this is one gamma function. These gamma functions divided by this is another complex gamma function. And this is third gamma function, also a complex gamma function. That's why it's very convenient to object. And then this formula simplifies, but I will give immediately even more complicated form of the same relation. Namely, I apply the general linear fraction transformation to all variables, including the integration variable. And then this integral, exactly computable integral, is converted to the following relation. So now you have product of three these kinematical factors, powers of these complex variables, alpha, beta, and gamma, and alpha, beta, and gamma satisfy this well, a kind of balancing condition. And the result is that this exactly computable. It's the product of three complex gamma functions divided by this kinematic factor. People from conformal field theory know this object perfectly well. It's conformal triangle and also called star triangle relation. And Derkachov, Monotreme, and Valenevich have found the Mellin-Barnes analog equivalent form of this relation, and has the following form. So you introduce now, instead of integration over complex plane, you have now infinite bilateral sum of contour integrals of Mellin-Barnes type of the product of, in this case, 6 complex gamma functions. Here they are. And the parameterization is evident because all this alpha, beta, and gamma are related to this parameters Sj, N, and J, which are the parameterizing these three complex variables. And here is the balancing condition. So sum of these Nj's and Mj's, which enter different pieces of this relation, is 0, and sum of these continuous parameters, actually in complex parameters, equals to -2a. So this is the relation which shows you the richness of the thing, because this relation was used many times in quantum field theory, and I will not mention, not to lose time, but somehow it's very popular and widely used relation. The thing which I would like to mention is the fact that the measures of such type of das Mellin-Barnes were introduced already by Naimark in 1959 when he was considering 3J symbols for SL2C group, and you will see that in the Planck formula which he derived there exactly merges this type of measure, infinite bilateral sum of Mellin-Barnes type of contours. So it goes back to very old times. Now, what about my subject? It's the following one. Now I would like to show that these objects emerge from the hyperbolic level in the following limit. Formally, this limit was described by Bazhanov, Mazgayev, and Sergeyev, but rigorously with full derivation. They just gave the formula without any explanation, and full derivation rigorously was given in our work by Sarkisyan. So this ratio of two infinite products, you parameterize the ratio of omega 1, omega 2 as I plus some delta, and take the limit delta goes to 0. Then for 2D CFT theory, this is a constraint. This corresponds to the limit when central charge goes to 1. For the special choice of this variable u, the argument of this function, which is given here, the normalized, when n, the leading thing, is integer, it's very important, and the subleading term is complex, then when you insert it here and take this limit, then I will skip the derivation. I don't have time. Interested people can look at the slides when they will be posted. But the result is as follows. It's interesting derivation because, for instance, it uses the following formula. You have the ratio of the Dedekind zeta functions, the modular transformation of that function, which has, this is the just modular transformation of the Dedekind zeta function. And in this limit, you have to use it when both q and q tilde go to 1, and it gets a very cute phase factor exponential of pi over 12. So it's 24th root of unity. The result is as follows. In this particular parameterization and limit, this hyperbolic gamma function diverges. Here is the divergent factor. Delta goes to 0, and the rate of divergence depends on the value of x. times some exponential, again, root of unity, and times the complex gamma function. That's it. And from the result of Eric Ryan's on this uniformness of the Q gamma function by Jackson on the uniformness of this limit. The same is applied here. This limit is uniform, and so we can apply this relation, this asymptotics to the integrals and get new identities. So how it works? So now I take this hyperbolic integral, which I described earlier, and parameterize there the integration variable in a similar way, the parameters in a similar way, and again take this delta goes to 0. The point is that here now, very important, that this n which enters here and j which enters here, they may be both integer and half integer. Why? Because they enter in the final result only in the combination when they either sums or differences, and therefore, and only these objects must be integer in order to apply the previously described limit. And this implies that this n and this nj may be half integers, and I introduce new variable nu, which is either 0 or 1/2. And then applying this asymptotic formula for the hyperbolic gamma function, here's the result. Again, some diverging factor, and this hyperbolic integral is reduced now to this complex hypergeometric integral in the Berlin-Barnes form. Infinite bilateral sum over the integer n times integral. I converted the turned 90 degrees the control integration, and so it is now 16 complex gamma functions in this piece, in this place, and this piece, very simple rational piece, emerged from the limit of the product of the hyperbolic gamma functions which were sitting in the denominator. So here's the explanation of the skewed factor, because in this case, this is the ratio again to complex gamma functions, but it is simplified due to the properties of the gamma function. And the important thing is that we have now two balancing conditions separately for continuous variables and which enter here as subleading asymptotics, and for integers which enter here as in this parameterization. And so here's the result. So it's integral definition and the balancing condition and the equation. So here's what happens. You will get from the analytic difference equation of the second order now the recurrence relation and the finite difference equation in different variables. So in these integer variables, which were emerged, you've seen already, you will have the recurrence relation. And for the complex variables, you will get the finite difference equations. You see, the coefficient b, it's exactly the same as before, as in this rational limit number 1. So I will show it to you. Here it is. So here is, so you have exactly the same looking equation as this one. But there is a principal difference from this one, and it goes as follows. So the coefficient is this one, and the parameters alpha k are now parameterized as follows. So I as k, this complex piece, minus integer divided over 2. And the equations now, as I see, it is in continuous variables. You shift by I, or plus I, or minus I, but in integers, you shift by -1 or +1. Formally, these shifts are equivalent to the condition that alpha 6 is changed to alpha 6 plus 1. Just look at this expression and see what does it do. But you cannot interpret this equation as an analytic difference equation in the variables alpha k. Here is the explicit solution of this equation, which explicitly shows you that nk and sk enter in a completely different way in the function. So what we have here, this is not an analytic difference equation in the variables which enter the potentials. It's the potentials because of the complexity and the things split into the real in this if sk is real complex part and so imaginary part. And somehow this is quite, to my mind, very new phenomenon in this analytic difference equations theory, because you are starting from analytic difference equation to very specific limit, and suddenly you get the same looking, similarly looking equation, which is not analytic difference anymore in the parameters entering the potential, the coefficients. And what happens with the second equation, which shows actually what's going on? The second equation, second hyperbolic equation, is converted again to the same form of equation. Here it is. Again, the potential is exactly the same, but parameterization is different. You see here we had minus nk, and here we have plus nk. So you see the second equation exactly splits this real and purely imaginary part of the parameters. And so this f curled f function satisfies these two equations. And together they exactly show you why these are not analytic difference equations in these alpha variables, but a mixture of recurrence and analytic difference equations. The third limit, this is not the end of the story, so there is a continuation of that. Namely, we have found with Gore a new degeneration of this hyperbolic gamma function, and it goes to the limit when b, this conformal CFT, 2D CFT parameter b, when it goes to 1. Again, parameterization 1 plus I delta, this is sublinear asymptotics, and corresponds to the central charge going to 25, because b goes to 1, so it's 24 plus 1, 25. And if you take the argument of the hyperbolic gamma function in generic position, then nothing happens. So it remains finite, meromorphic function, no problems. But for the very special choice of the argument, here it is. This is the choice of the argument of this hyperbolic gamma function. Again, the leading asymptotics is normalized to some integer and sublinked to some complex variable y. And the limit is that, again, it either diverges when n is negative, or vanishes when n is positive, and times again some root of unity, and this is standard Pohammer symbol. You see, earlier we had the ratio of gamma functions, not trivial complex gamma functions, and this ratio of gamma functions in this case is converted to the standard Pohammer symbol. Here is the definition. And so that's the limit for the gamma function. And now I apply it to the integrals. Again, some cute parameterization of the variables, integration variable or parameters. Again, some this half integer new parameter images. And here's the asymptotics. So this integral, hyperbolic integral, goes again, blows up to some constant. And here's the answer. What you get instead? This is R. You see, I explicitly wrote it, that it is the rational function. We got the rational function, but the representation of this rational function is extremely unusual. So you have the infinite looking as infinite bilateral sum of integer n and the sum of Mellin-Barnes contour integrals of the following expression. So this you know already. This is a simple factor rational one. And here is the product of Pohammer symbols, depending in a specific way on these integers and complex variables sk, and these are summation and integration variables. The important thing is that you see these Pohammer symbols have either positive or negative values, which means that sometimes they sit in the numerator, sometimes in the denominator. And the balancing condition, again, is split into two pieces. So you have now the balancing condition of this form. Why it is rational, this function? The very simple argument. For sufficiently large this variable n, it damps this n case. So all the Pohammer symbols start to have one positive or negative indices for sufficiently large n. And it means that all the singularities of these integrals lie on the one side of the integration contour, either to the right or to the left. And so it means that it vanishes, these integrals. Therefore, only for finitely many nks, you have these non-zero contributions, and for finitely many n's, not nks. And when it's finite, you immediately see that this is just the rational function. You integrate rational function over the infinite contour. When you close it up, and you will get another rational function. So this is the rational function with very unusual representation. And the equation again starts to be the same. They have the same form as before. Now R curled is the ratio of this R bold divided by 4 Pohammer symbols, and the B function, again, B potential is again exactly the same for specific parameterization of these alpha variables. So everything looks more or less the same, just interpretations are different and choices of the parameters are different. Then the second hyperbolic equation is converted to this one. So again, two equations satisfied by this one function. Okay, that's the rather detailed description of the story. Sorry for the technicalities, but that's a life. What can we do? Now I turn how to apply to the question how to apply these limits I described at the very particular, very explicit equation to the Rusinar's and Van Degen elliptic and body problems. So here is the Rusinar's Hamiltonian, and everyone know it perfectly well, and T's are just q-scaling operators, so nothing to comment. Everything is well known. The Van Degen Hamiltonian has the following form. So it's now sum of T and T inverse times some potential, and the potential has the following form. And if you remember the coefficients which I was describing for the elliptic hypergeometric equation, then you will see that this piece is exactly looking similar to what I described for this elliptic hypergeometric equation. And this piece it's a mixture of integration variables, so it's intertwines, so it makes the situation non-trivial from the n-body point of view. So I will not describe what is the potential V. There are no any constraints for the parameters Tj. This V function is very complicated. I will not need it because I immediately impose the following constraint, the balancing constraint. And then in this case, this Hamiltonian gets simplified, and in particular, the potentials become elliptic, p-elliptic, and it has, again, the same form. But now you see it's factorized. V disappeared. You have this t minus 1 and t inverse minus 1, which means that the constant is the eigenfunction of this Hamiltonian. It will be important in the end. So I stress it immediately here. This factorization representation is very nice for understanding that the constant is eigenfunction, and later you will see what I will use it for. If you take n equal to 1, then here is the explicit form of this eigenvalue problem for this Hamiltonian. Now, no big imagination to see that if you impose, and you see the balancing conditions there, comparing with the elliptic hypergeometric equation in the symmetric form, you immediately recognize that if you impose constraint and choose the eigenvalue of this form, then you will get from this equation the elliptic hypergeometric equation. So it's immersed into this system, to this eigenvalue problem. And using now the things I described for the elliptic hypergeometric function, I lift all these things up to the full level, to the full model of Van Degen and Rusinar's. We'll see what it will mean. So if I take this elliptic hypergeometric equation in the symmetric form and now reduce this symmetric form to this elliptic complex hypergeometric function level, so it's a rational reduction number 2, I will get this equation. The coefficients are now rational. Split of the argument now into the continuous and discrete piece. This is evident. The balancing condition has this form, and this is the constraint which I described that it must exist at the elliptic hypergeometric level. However, the parameterization of these betas and integration variables, this variable z, which is external variable for equation, is this one. So gammas are continuous variables, rj's are discrete variables. And you see they again have this nu, which is integer or half integer. And for this particular pieces, again, you have the split of the balancing condition into 2 parts. So you have sums of r is 0 and sums of gammas minus 4a. And so what I will do, I will take this equation and remove now this constraint, just throw it away, this constraint, and replace this product, which is sitting here, by arbitrary lambda eigenvalue. And what I will get the representation of n equal 1 Van Degen Hamiltonian in this complex hypergeometric setting. You see, this is a new rational model which emerged. This will be new. This is a new rational model because the potentials are the same as before, as in the previously investigated by Van Degen himself, the rational degeneration. But now interpretation is completely different, and the measure I will describe it will be completely different. And here is the complementary thing. Let's discuss the measure, the scalar products for eigenfunctions of the general Van Degen Hamiltonian eigenvalue problem. And I introduce the scalar product with the help of this now elliptic hypergeometric integrals. So if you remove phi and psi, this will be just the Cn analog of the V function. introduced by Rines. I did it only in the rank 1 case, and he described it at the general rank case. And the point is that the general one division Hamiltonian is Hermitian with respect to this measure, with respect to this scalar product. Very important fact. Now I apply the machinery of reducing full machinery hierarchy of reductions towards the complex hypergeometric level. So I jump immediately to the end. And here is the scalar product at the rational limit number 2. So it's now sums of integer variables. So again, measure is split into the discrete summation and integration contours. This is the product of the eigenfunctions at the rational level. Here is the mixture part. This is the ratio of complex gamma functions. And this is, again, the product of gamma functions. And this is also a product of gamma functions. So this is the scalar product. Remember, no any balancing condition, because I'm talking about fully general one division model, no any constraint. But in order to say something additional, I would like to now to talk about Hamiltonians. So how the Hamiltonians change? So for instance, in the Rusinai's case, this looks like a rational degeneration of the Rusinai's model, because you have rational coefficient. And if I replace this T operator, which is operator which shifts continuous variables in one direction and discrete in another direction, by standard shift operators of T, this will be the well-known rational generation of one division model. But the interpretation now is very different. And in the one division case, it becomes even more interesting, because here is the Hamiltonian. And in order to have such a picture, I have to impose the balancing condition. You see, I give the factorized form of the Hamiltonian. Again, the coefficients are rational, these B coefficients, but this T operator is now, as I said, it shifts continuous variables in one direction, discrete in another direction. Otherwise, it's looking precisely the same. And Z variables are now split into the imaginary part and discrete part. Beta is analog of T, so beta K is these variables, 8 variables. And the balancing condition now is split into 2 pieces, having the following form. So for continuous variables is this one, and for discrete variables, I have this one. And one can check that this Hamiltonian is Hermitian with respect to the measure which I introduced in the previous slide. And so everything works rather well. Actually, this relation is true for fully general, I would like to say, one division Hamiltonian. You just, I need this for this representation, but I can abandon it. It will be the same. This Hermistic condition will be true for generic case when I work with this integral without any constraint. But the interesting thing for me will be when I impose this balancing condition. And what is interesting in this case? It's the relation to Zellberg integrals. Namely, if I impose, so if I take this elliptic one division model factorized with the balancing condition and impose one more constraint, namely I remove 2 parameters, T7 and T8, the product equals to PQ, then 2 elliptic gamma functions drop out from this normalization of these wave functions. You see, I took as the wave function this unit. So as I said, it's for the factorized form, it's the eigenfunction. So what I'm talking about norm of the simplest eigenfunction which I can find here, it's a unity. And it's given by elliptic Zellberg integral, which was well described by Ole Warnar in his talk. And it has the following form. So some products of ratios of elliptic gamma functions which admit explicit evaluation, which the thing which we introduced by one division, which was proved by some other people, which Ole mentioned in detail. What goes on at the rational level, which is interesting to me? It's the following. So I get now take, because of the factorization of the Hamiltonian, this one is again the eigenfunction. So I look for the norm of this eigenfunction after imposing these constraints for the gammas, for 2 gammas and for 2 integers and 7. And it should be actually not some mixed up. Okay, here it should be R's. I forgot to replace these N's by R's. It's just the fault in preparation, which I actually finished the preparation of talk just half an hour before the talk or before the session. Very difficult times nowadays, so I'm barely able to prepare this talk. Sorry about this. And so what I have again the same situation. This measure falls down into the following integral. Now I have not 8 but 6 only parameters, gamma L, M, and L. And this is now again computable integral and well, sum of integrals. And the final right hand side has the following form. It's again the ratio of products of complex gamma functions with very specific parameterizations. And you have this now balancing condition of the form. It's split into 2 pieces as usual. And this is new rational generalization of the famous Zelberg integral. And somehow it should contain the Mellin-Barnes forms of the results which you obtained long ago by Dotsenko, Fateev, and Aomota. They considered this complex analog of the Zelberg integral, standard Zelberg integral. So a generalization of this Gelfand, Greif, Vilenkin formula which I described. So they lifted it to the CN root system and we have found analogs of that. But they gave it in the form of the integral of complex planes. And this is the Mellin-Barnes form. So it should comprise what would be analog of that. It's a result work in progress, but it is more general, of course. There are more parameters. Okay, that's all I wanted to say. And thank you for the attention. Sorry for some difficulties in presentation. And please pose your questions if you have. Hello, do you hear me at all? Hello?
Sorry, if I could ask them a question.
Yes.
Takemura considered certain degenerations of the Fandian model as well to get to what he called the Q-Horn equations. This is, I think, at the trigonometric level, so not the rational case, but I'm wondering if you have considered such limits or degenerations of the elliptic hypergeometric integrals.
Yes, in a sense, yes, in a sense, no, because the systems which we have described, they are most general. They are upper. I would not claim that what Nakamura did, not Nakamura, but what's the name was?
Takemura. Sorry.
Takemura, yes, sorry, yes, of course, Takemura-san. He did, but I'm sure it is contained, definitely contained in this picture. And to my mind, it lies lower. We did not compare it. Sorry about that, but I know the situation. It's a degeneration of this equation. And what's the biggest difference is that he considered the rational limit number 1. And I described the rational limit number 2, and they did not consider at all a rational limit number 3. It's again a separate story. But what at the complex hypergeometric level is completely new story. So it's Takemura's results can be repeated now at this level, at the level of complex hypergeometric functions, and it will be again some kind of Hohen equations or Q-Hohens if you work with the higher things.
I see. Thank you.
More questions, maybe.
Slava, I also have a question.
Sorry, Jan Filipe, okay.
Yeah, sorry. So in the rational limit, finally, I mean, you're coming from the elliptic level, but can you, know the answers, your rational formulas, can you prove them, could you prove them, for instance, also completely independently using only stuff of ordinary gamma functions and I mean, or is it really necessary to pass through the elliptic level to prove these formulas?
I have the answer, delivered. The answer is as follows. Yes, you have to develop the technique for use at the standard plane hypergeometry or Q hypergeometry to get such type of results. But it is very complicated. You have to look the papers by Derkachov and Manashov. They established certain identities they generalized the Gustafsson integrals and relations for them to the complex hypergeometric level of type 1. And they did it from scratch, as you wanted. some determinant representations for integrals, evaluation, some tricks, and so on. Everything from scratch, no any limits, as you want. And they did, but it's very complicated. First and second, they couldn't go beyond the computable cases. So they have reproduced only complex analogs of the computable Gustafson integrals. As to the symmetry transformations, they cannot do it. And but in our approach, when you reduce through this limiting procedure, it goes immediately at the huge number of cases, as you understand, because we have a sea of tractable elliptic hypergeometric integrals in symmetry relations for them. And now through this sea of limits, you get C in the power C of possibilities to get to land at different relations. And so everything will be rigorous. But there must be, of course, a way to do it from scratch, as I said, by using the technique which Derkachov and Manashov have developed. Did I answer?
Okay. Yeah. Thank you. Then I know where to look. That was actually my question. Yes. But I have a second question. Could you show again just the Rauscheners, this complex rational Rauscheners?
Do you see my screen?
I see your screen. Yes.
Okay. Then just let me go.
That was one of the last.
Yes, here it is. Yes, this Hamiltonian, I guess.
Yeah, sure. So, so these U's and so you've written disease in the real and imaginary part, but can you not write these actions as simply the complex as a rational Rauscheners system which shifts in the z variables of a complex shift, of a complex step parameter, if you like, because that's finally what's going to happen, right, or not? Or is it missing something?
I think no. You see, the point is that this function satisfies not one, but two different. It looks like yes, because as I said, the parameters. You see, all you need, if you replace this t by scaling, that's it. Or shift, plane shift, complex shift. You will get it, but you cannot do it. You see, the measure which you use for describing the eigenfunctions of these objects. This is not horrible, but here it is. I described it. The point is that the measure is completely different. Here it is for your model. For your model, look how the measure looks. You cannot describe it, at least at this in this setting, as the complex. As you see, complex sheets, and somehow the measure is very different. So
okay.
You see,
of course,
I cannot answer.
That's one step further, right? The measure.
Yeah.
For instance, if I would like to know if these operators, these rational Rauscheners operators commute, it just follows from the ordinary commutativity, right?
Yes, evidently, because you just replaced the shifting parameter operators by peculiar objects. That's it.
Yeah.
Philip, I can answer. I can say more a little bit. The point is that the work in progress, we somehow plan to clarify the situation with this relation with the integrals over complex planes. This Amoto thing, the Tsenko-Fateev thing. So we need to find the analogs of all these things with this, which I described at the level of complex integration measure. You see. And then look what it means there. This is not done
I
yet.
see.
So, and therefore, I will not say immediately that no, it's not possible. But at this picture, I do not see any possibility. Everything is split. Equations, explicit solutions you have, they satisfy two different equations where you have different parameterizations of the variables. So you shift continuous in one variable, shift discrete in one case, but for second equation in the opposite. So you can both describe using one variable. You see, so somehow strange. I don't know at the moment, but hopefully we will clarify this a little later. For the moment, it looks like I described.
Okay. Yeah. Thank you.
Okay, it's somehow time. other further questions? Oh, I managed to give the talk just in 1 hour. Okay, very good. And if no further questions, then I stop sharing my screen and turn now to the audience we have. Okay, let's conclude the workshop. Peter is away. He had to run for some urgent affairs, so I'm replacing him. I would like to thank all the participants for coming, for giving talks, and that's very good in the sense that in this very terrible times, it somehow shows that the life continues. And 1 week ago, I was even thinking to cancel my participation in the talk, but somehow it started to be very, how to say, so basically, not to lose my mind, I have realized that I have to work.